start making them until after I finally got to tell her I was there. I don't know why they do that. So section 10.6 is called the counting. That's all this section's called, counting. Okay. And it's the application of ways of finding the number of objects in a collection or different outcomes in a situation. So the first couple of problems that we're doing uses what they call the fundamental counting principle, or just counting. So like have you all been to schools where you've had a combination lock before, where you had to like turn, you had 3 different numbers on the combination lock?
Yeah.
You had so many choices for your first number, however many numbers were on the dial, you had that number of choices for the second number, you had that number of choices for the third number. So you have a whole bunch of combinations for one single combination lock. So that's the kind of things we're going to be dealing with for number 1, 2, and 3. Same thing with license plates. They use the alphabet and they use numbers. And so they use different combinations of letters from the alphabet and numbers to get all these different possible combinations for license plate numbers, so everybody's license plate's different. Okay, so those are the types of problems that we're going to begin with using the counting principle. So basically what it says is you take the number of options for each thing. Like you have, how many letters are in the alphabet?
26.
26. So you have 26 choices for the first letter in the license plate. Then you'd have 26 choices for the second letter in the license plate, 26 choices for the third letter. So you have 26 for all 3 letters, and then you multiply those together to get the possible combinations. Okay, so that's what you do. You take the number of possible ones for each individual section and you multiply them together. So like I said, we're on page 486 is where the problems are. We're doing the teals. So even though it says 1 through 52, okay, if you look, there's not a whole lot of them that they have in teal. Okay, so even though you think, oh my goodness, there's a lot of problems, we're still not doing a whole lot of problems. So we're starting on the word problems, where it says solve each problem using the multiplication rule for counting, or what they sometimes call the fundamental counting principle. Okay?
Fundamentals.
So we're on number 1. It says a normal PIN, personal identification number, for a bank card has 4 numbers with 10 possibilities per number. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 that you could use for your first digit of your PIN. Then 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 that you could use for the second digit of your PIN. Third digit and fourth digit, okay? So we have 4 digits in our PIN. So there's 4 blanks that we have to fill in, okay? The choices for each one are 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, or they said is how many possibilities? 10 possibilities for each one. How many different possible pins can be created? Because it says you can repeat the numbers. So that means I could have my pin number as 5555. That's not a very smart pin, okay? You don't want to do that, but you could have it as 5555.
My pin number is 1, 2, 3, 4.
Okay, or yeah, that I know. Like the old flip cell phones, they always started off. That was their lock code was 1, 2, 3, 4, and some people didn't change it. But anyway, you always have 10 digits for each one. So I have 10 choices for the first digit, 10 for the second, 10 for the third, and 10 for the fourth. So all I do is I just multiply that together. 10 times 10 times 10 times 10. So how many different possible PIN number combinations are there for your bank card?
$10,000.
Huh?
10,000.
10,000, he says. Do y'all agree with him? 10 times 10 times 10 times 10. Yes? Does everybody have a handy dandy calculator? Remember, these things are your friend if you have one. All right. So 10 times 10 times 10 times 10. It's pretty easy. Yes?
Yeah.
Okay. Now, number. Let's see.
There goes Marquis.
Was that Marquis?
Yeah.
Well, kind of. Okay. Well, maybe. Right, maybe. All right. We're on page 486, and we've only done number 1, so you haven't missed too much.
Okay.
Okay. So on there, because it said they could be repeated. Now, if it said they couldn't be repeated, then that gets us into another situation. Okay. If it says they can't be repeated, do I still have 10 choices for everyone?
No.
No. I would only have 10 choices for this one. I would have 9 choices for this one because I couldn't use this number again, whatever it was. I would have 8 choices for this one because I couldn't use either one of these numbers again. And 7 for this one. So it would have to count down each time because you couldn't use the same number. So for example, if I said my first number was a 3, then I can't use 3 anymore. So then my next number could be 0, 1, 2, 4, 5, 6, 7, 8, or 9. So let's say it was a 7. I couldn't use either one of those. So each time my number of choices would count down. I couldn't use it again. Okay? But if it says they can be repeated, then that stays the same all the way across. Number 2, let's read that one. It says the electronic lock to a particular safe uses 4 letters. So we have 4 letters to start with. Okay. So these are all letters. And then it says followed by 4 numbers. And these are all numbers. Okay. So the first 4 are letters and the second 4 are numbers. Assuming that the letters and the numbers can be repeated, how many different passwords are possible? So again, remember I told you before, it kind of helps if you know how many letters are in the alphabet, how many different digits there are, because when we're talking about digits for numbers, you start with 0 and you go through 9. It's single digits, not getting into higher numbers. So for my letters, there's how many letters in the alphabet?
26.
So the first 4 blanks, I have 26 choices for each of these first ones. Because I could use A, I could use A, I could use A, I could use A. It didn't matter if they were repeated. But there's 26 possible letters that I can choose from for the first 4 blanks for the safe code. For the last 4, they're numbers. So our digits, again, were 0 through 9. So that's 10 digits to choose from. So I got 10 choices, 10 choices, 10 choices, 10 choices. So if you haven't figured it out yet, are there a lot of possible safe combinations you could have?
Yes.
Yes, there's a whole lot because these are big numbers. Because just when we multiplied the 10s in number 1, we got 10,000. But now I have to multiply that by 26 times 26 times 26 times 26. So you're going to get a really big number. So is everybody multiplying that out and getting a real big number?
Yep.
Yeah? They got a real big number? Who else made it? Or who left? What happened?
I lagged out.
Well, why?
I don't know. There's something going on with my internet.
Okay. All right. So we multiply all these together and you get a 4, a 5, a 6, a 9, a 7, a 6, a 0, a 0, a 0, a 0. So
That's my kind of password.
huh?
But that's my kind of password.
There is 4,569,760,000 possible combinations for that safe if they allow letters and numbers to be repeated. Okay, so As you can see, you can have a lot of answers on these. Okay, last one of this type, number 3. Number 3 says the lock on a particular briefcase uses 3 numbers. So I got my 3 numbers. You'll notice as I'm reading it, I'll put it down so I kind of get an idea of what I'm doing. Assuming that the numbers can be repeated, how many different 3-digit numbers can be created for the briefcase? So remember our numbers 0 through 9, so we have 10 possibilities for each one. So 10 times 10 times 10.
1,000.
That's going to be 1,000. So just for for the briefcase, you know, a lot of times they'll have those little dials that you roll up and down with the digits to get the numbers. There's 1,000 different combinations of the code you can put on those. Okay. I got that one. Pretty easy.
Yeah.
We multiply our possibilities. Now, when we are multiplying these possibilities, what it gets us into is, remember I talked about earlier about the repeating, that if things can't be repeated, it counts down the number of choices you have for each one. Okay, so like for this same one, for number 3, if they couldn't be repeated, I'd have 10 choices for the first one, 9 choices for the second one, and 8 choices for the third one. It's counting down, okay? This gets us into what we call a permutation. Permutation, it was on your notes, it's this formula right here, okay? This little exclamation point is also on your notes. That's called a factorial. It means you count down from that number to 1, and then you multiply all the factors together. So for example, if I gave you 5 factorial, that means you take 5 times 4 times 3 times 2 times 1 and get the answer. Okay? Now, if you have an actual scientific calculator at your home, it has the buttons that'll do that for you on there. Okay? I just got to see. Let me get where I can get in line. I forgot where they're at. Where's the factorial? And I don't see the factorial. Oh, it's up at the top. Whoops. 5 shifts. You know, if I could hit the right button, it would help. Yeah, okay. So on my scientific calculator, my little exclamation point is up here above my x to the -1. So it's way up here at the top. But it's in one of those little yellow ones where I have to hit shift and then the button. But when I do that, it puts the 5 and the exclamation point on my screen. And then when I hit equals, it multiplies all that out. And it gets 120. Now, for the permutation part, that button is one of the little shift things on my calculator as well. So how many of you do have a scientific calculator that you can use? Okay. If you look up above there, mine, it's above my multiplication and division sign. Above my multiplication sign is my permutation one. It has NPR, which is what they use for permutation. And then above my division sign, it has NCR, which is what we use for combination, which we'll get to in a minute. Okay, but the permutation is saying the order matters. Okay, so if I pick this one first, I don't have as many choices for the next one. I don't have as many choices for the next one. So the order matters. So like if you are saying people are running a race, there's 20 people in the race, how many people can come in first place? 20. After somebody's come in first place, how many are left to come in second place?
19.
19. How many are left to come in third place? 18. So it's going to keep counting down the number of possibilities for each place in the race. Okay, that's the permutation when it's mattering in order. Okay, if you are lining people up in line, You have first place, you have second place, you have third place. If you're arranging books on the shelf, you have the first one that goes on the shelf, then the second one, then the third one. So the books that you have left for each place counts down every time. Permutation, it's counting down. So on 7 through 21, on the teal problems in that section, this is our formula for permutation. The N stands for the total number that you have. Like there were 20 people in the race. There were 10 people in class. There are 15 books to put on the shelf. So the 10, the 20, the 15, those are our N. That's your total number. N is the total. R is the ones that are being picked, or the ones that you want. Okay? Those are the ones that are being picked, or the one that you want. N is the total number. R is how many that you're picking or selecting or doing. Okay? So, for number 7. Okay? It says 18P8. So remember, this first number is your N. The second number is your R. So all I'm doing is I'm plugging them into my formula here. So I have N factorial, or 18 factorial on top, and then 18 minus R, which was 8 factorial on the bottom. Okay? So think about what I said the factorial meant. Factorial meant you take that number and you count down to 1. So on the top, that would mean I had 18, 17, 16, times 15, times 14, times 13, times 12, times 11, times 10, times 9, times blah, 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 times 1. You would count all the way down from 18 to 1. And I'm not going to make you do that on these problems. I'm just showing you what it means. Okay? For the bottom, 18 minus 8 is what?
10.
10. So on the bottom, I have 10 factorial. So on the bottom, I would just have 10 times 9 times 8 times 7 times 6 and blah, 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 times 1. Okay? So remember, anytime you have something on the top and the same thing on the bottom, they're going to do what to each other?
Cancel.
Out. He's showing me on this calculator. So all of these from 10 down would cancel out. So what you're actually left with is just from the 18 down to 11. So you'd have the 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11. Or if your calculator has the nice little button and you found it, you put 18, you put your little NPR in, so it puts the little capital P on your screen. I hit something. All right, go back. So I have 18, I hit shift, my multiplication, and then 8. So it has 18P8. And then I hit equal, and it multiplies those numbers that I just listed out, 18 down to 11, and you get big answer. So it is 1,764,322,560. So 1,764,322,560. Okay, so in case you haven't figured it out yet, yes, we get big numbers on these.
Higgins.
So number 8, we're going to set it up. Number 8 says 13P6. So on the top, I would have 13 factorial. On the bottom, I would have 13 minus 6 factorial. Well, hopefully you all know 13 minus 6 is 7. So basically, I have 13 factorial divided by 7 factorial. So if I take, starting from 7 down, I know it's going to do what? It's going to cancel out, right? Just like we did up here, from 7 down would cancel out. So you're going to have 13 times 12 times 11 times 10 times 9 times the 8. and you get your answer. It's not quite as big on this one. This one's only in the millions instead of billions.
Yeah, it's a little baby.
I mean, it's still big, but it's not as big. Y'all getting that number? 1,235,520. Y'all getting that number?
Yeah.
Now, are these easier if you have the scientific calculator? Yes,
Absolutely.
absolutely, because you can just put 13, put the little P on the screen with the button, 6, and then it does it for you. If not, though, then you still only have to focus on this part that has to be multiplied together. It's just you got to be able to figure out what part gets multiplied together. So let's look at 17. 17 says 17 permutation 5. So it's 17 of them that I'm picking 5. Okay. So hopefully everybody knows 17 minus 5 is
12.
12. So since that means from 12 down, that part will cancel out. So I'm only left with 17, 16, 15, 14, and 13 to multiply together. Right?
Yeah.
So this one's even smaller.
Yeah.
Really? Did you do it?
No, miss. I just downloaded a new scientific calculator for this.
But can you multiply 17 times 16 times 15 times 14 times 13? I didn't clock back in. I didn't clock back in after lunch, after going to pick your all's lunch up. So 142,560 possibly. Yeah.
Wait, what? Oh, yeah. 742,000, yeah.
560. Okay, so those are permutations. Permutations, the order matters. Okay. Combinations are different. Combinations is like I'm just putting you all in groups. So it doesn't matter who I picked first for the group, who I picked second for the group.
Nah.
No, you're still in the group. Okay. Now, if I was lining you up, then it would matter who gets to go first, who goes second, who goes third. So that's a permutation. When I'm just putting you, okay, you three go over here and work on this problem. You three go over here. It doesn't matter who I said first over here, second over here, third over here. You're still in the same group together. So groups are combinations. When you're grouping it together and the order doesn't matter. So like if I was putting people on a committee, that's a combination. That's a combination. Okay? Okay. If I put it in if I'm putting people, like I said, on a team and there's no order for the team or whatever, then it's a combination. Everybody's still on the team, okay? If I was putting like baseball players in a batting order though, then would the order matter? Yes. So if
Yeah.
it's order, it's permutation. If it doesn't have order, it's combination,
Combination.
okay? So on the next section, we are doing combinations. Now you'll notice the formula is a little bit different for these. N is still your total number. R is still the number that you're picking or taking or using or selecting or whatever word they use in the problem. So you'll notice this part's all the same. N factorial on the top and N minus R factorial on the bottom. But since the order didn't matter, it has this extra little R factorial in the front that we can divide by, because that takes out all the duplicates of getting the same people just because they were picked in different order. So for number 25, we have the combination of 13 combination 5, right? So I'm plugging into the formula. 13 factorial on the top, 5 factorial on the bottom, and then 13 minus 5 factorial on the bottom. Okay. Then that becomes 13 factorial on the top, 5 factorial, and 13 minus 5 is 8 factorial on the bottom, right? Everybody agree 13 minus 5 is 8?
Yeah.
Hi, Jazaria. Y'all been fighting internet all day, haven't you? We're on page 486. Okay, so 13 minus 5 is 8. So this is what I have so far. Now remember what we did on our permutation ones. I had 13 here and 8 here. So when I lined all those up and canceled them out, from 8 down is going to cancel out with the top on here. So I'm actually going to be left on the top with just 13, 12, 11, 10, and 9. Because 8 down would cancel out, correct? Yes?
Yeah.
Okay. On the bottom, I have 5 factorial still. So I have 5 times 4 times 3 times 2 times 1. Now, you can do this a couple of different ways. You can look for things that'll cancel out. For example, I know 4 times 3 is what?
12.
12. So if I take 4 and 3, I can cancel out the 12. Because remember, if you find stuff on the bottom and the top that's the same, you cancel out. What can I do with 5 times 2? What's 5 times 2?
10.
10, so I can cancel out the 10. So the only thing left on the bottom is 1, and the only thing left on the top is 13 times 11 times 9. So that's what I need to multiply together now to get my final answer. So your combination answers are going to be smaller than your permutation answers, because the combination answers, you're dividing by that extra thing where the order doesn't matter, so you're going to get smaller numbers for the combination part. So when I multiply the 13, the 11, and the 9 that was left, I only get 1,287 possibles for that one. Okay, so when we were doing permutations, we were getting answers in the billions and 100,000s and millions, okay? When you're doing combinations, they're going to be smaller, okay? So that was number 25. We plug it into the formula. If you don't have the scientific calculator with the little NPR button or the NCR button, then you've got to kind of work it out like I am up here on the board, seeing what you can cancel out to get smaller numbers to multiply, because that's going to be your best bet. Okay? Now we're ready for number 26. Number 26 says 14 combination 9. So when we're doing combination, this is our formula for combination. Okay? So I have 14 factorial on the top, 9 factorial times 14 minus 9 factorial on the bottom. The first number, remember, is the N. The second number is the R. You plug them in accordingly into the formula. Okay? Now, I'm going to see what I can cancel. But first, I got to do 14 factorial still on the top, 9 factorial on the bottom, and then 14 minus 9 is 5, so I have 5 factorial on the bottom. Now, I want to try to simplify the best way I can. Okay? Now, on number 25, I went ahead and canceled out the 13 factorial with the 8 factorial from the bottom to get 13, 12, 11, 10, and 9 left on the top. Okay? Because this is the bigger number. On this one, my bigger number is in the front. It's the 9 factorial. So I'm still going to cancel that out. I'm going to get rid of the 9, 10, 8, 7, 6, 5, 4, 3, 2, 1. So what's 14? If I take out the 9 into that, I have 14, 13, 12, 11, and 10 left on the top. And then for 5 factorial, 5, 4, 3, 2, 1. So I'm going to do similar to what I did on 25 for canceling out. 4 times 3 cancels out the 12. 5 and 2 cancel out the 10. So basically I'm left with 14 times 13 times 11. So if you've got the button on your calculator, you would just type 14, use the shift button to get the C and the 9 and hit equals, and you get the nice answer. If you can't do that, you see what you can cancel with the factorials and then multiply what's left, and you still get the same answer. Somebody tell me what we're getting for the answer?
2002.
There's 2002 possible combinations of having, let's say, 14 people and putting them in a group, picking 9 for a group. That's what that means. You have 14 people, I'm picking 9 of them for a team. So there's 2002 possible ways I could pick the 9 people from the 14. Okay?
Dang.
That's the way the combinations work. But if it was the permutation where we were doing it in order, it would be even what? Bigger. Okay? Now, I skipped down to number 39. Number 39 says 18 combination 6. Is that right? 18 combination 6. Okay?
Yes.
So here's what we're going to do. 18 is my N, so I have 18 factorial. 6 is my R, 6 factorial. And then 18 minus 6 in parentheses, factorial. So I just plug them into the formula. So then that's going to simplify 18 factorial over 6 factorial. And then 18 minus 6 is
12.
12 factorial. So you're going to take whichever one of these is larger in the denominator, and that's the one you're going to cancel out into the numerator first. Now remember, we don't want to have to list them all out like I started showing you on number 7 here. Listing them all out so you can see what crosses out. Okay? You just kind of have to use your brain a little bit. If this is 12 factorial, 12 times 11 times 10 times 9. So if I'm canceling that into that, I'm left with 18, 17, 16, 15, 14, 13. Everything down to where I start getting to the 12. Okay, everything that would have been in front of 12 is still going to be there. From 12 down would have canceled out. On the bottom, I have 6 times 5 times 4 times 3 times 2 times 1. You look for things that you can cancel, okay? You look for things that you can cancel. What's something that I can cancel out from the bottom and the top? Anybody?
6 times 3.
6 times 3 would cancel out the 18.
18.
Okay. Now, I'm not going to be able to cancel anything with 17. 17 is a prime number, so that one's still going to be there. But for 16, is there something that goes into 16?
4.
4. What else? What could I also use the 2 there?
Yeah.
What's 4 times 2?
8.
4 times 2 is 8. 8 goes into 16, so that becomes just a 2 left. Can I do something with the 5?
Catching. 15.
15.
3 times.
Okay. So the only thing that I'm left with on the bottom is 1, which is good. You don't have to divide by anything. On the top, I'm left with multiplying 7 times 2 times 3 times 14 times 13. And then getting your answer. I know. Does anybody else know?
I know.
Anybody else other than Micah and myself?
Pick me.
Wait, what?
I know.
Closer. Everybody see?
Yes.
Is it 18,564?
You should,
Mm,
right? And that what it was? I thought that's what I had. Yeah. Okay. Yep, that was right. We're good. Okay, so those are combinations. Okay, so which one does order matter?
yes.
Which one does order matter? Permutation or combination?
Huh? Permutation.
Permutation. The way I remember it is permutation, you're putting them in place. In a place, they're in order. Okay, permutation, they're getting in a set place. Combination is just a collection. So they're just all together. It doesn't matter what order they're in. Okay, so order matters for permutation. Order does not matter on combination. Okay,
Yeah.
there are 4 that we skipped. Okay, that you all have to go back and try on your own, and we'll check those answers tomorrow. Okay, does everybody see which ones we skipped?
43, 49, 47, 51.
We skipped 11 and 21. I'll put them down here. We skipped number 11, number 21, number 29, and number 35. Those are the ones that we skipped that you'll have to go back and do. Okay?
Oh man.
Oh man. All right. Yeah, let's set up our lovely word problems, everybody's favorite. Okay? So, on number 43, it says a chess club has 55 members. They are going to elect 3 officers, president, vice president, and treasurer. So since you have 3 officers, do the offices have like a prominence or an order?
Yes.
President's first, then vice president, then treasurer, okay? So they have an order. So is that a permutation or a combination?
Permutation.
Permutation. So to set it up, there are 55 members,
Jeez.
and it's a permutation, and they are picking 3 for the officers. So it's 55.
Banging.
And then you would just have to work that out.
Chess code got it banging.
Okay. Everybody remember that?
Yeah.
Right now, we're just getting them set up, figuring out whether they're permutation or combination. Number
Okay.
4. It says a team is voting to pick 3 roles on the team: captain, co-captain, and assistant coach. If the team has 30 players, how many different arrangements of players could they choose? Again, do you have like a priority level for those?
Yes.
Captain, co-captain, assistant coach. So there's 30 people, permutation 3. Okay. Now we're on page 487. We're doing the last 3. We're just getting these set up. Okay, as long as you know which one it is, permutation or combination. 47 says, a youth pastor needs 4 members of the youth group to assist him with cleaning the church. There are 50 teens in the youth group. How many different groups of people could he select? So is that a permutation or a combination?
Combination.
Combination.
Combination, because does it matter what order you pick them?
No.
No, they're all going to be picked to clean the church. Okay? He's picking them all to still clean the church. So I have 40, and I'm picking there's 50 people, and he's picking 4, I think, to help him. Yeah.
Yep.
So it's 50, combination 4. All right. Yes, we're good with that? Okay. 51. A director is trying to cast 3 people into different roles: protagonist, antagonist, and understudy. If 40 people tried out for the play, how many different ways could the director fill the roles? So is there a set order for those?
Yeah.
Yes.
Set roles in the play. So permutation or combination?
Permutation.
Permutation.
So it's 40, permutation 3. And then 52, a customer has to choose 3 security questions for his internet account on a particular website. There are 10 options of security questions for him to choose. How many different combinations of security questions are there? So does it matter what order the questions are in?
Yes.
No, it doesn't.
No.
They don't care what order the questions are in. So it's 10 questions to choose from, and he has to pick how many?
3.
3. So it's 10, combination 3. Okay. So we got all 4 of these set up, right? Yes. You have to at least answer number 43 and 52. Okay. So you only have to get the final answer for those 2, plus make sure you did these 4. Okay, and then we'll talk about those 6 answers tomorrow, and then we'll review this so we can do our quiz over counting, permutations, and combinations. Okay?
Alrighty.
All right, and then we'll talk more about, some of you have been sending work to me, and most of you, I could read it. Some of you, I don't know, I couldn't read it. So some of you haven't sent anything yet, so we'll talk about that some more, because throughout the week, I want to try to get where I've seen everybody's work, so I can get all that in since we're finishing up the week. We're finishing up the chapter. All right, so make sure you've got those 6 done for me for tomorrow, and we'll check those answers tomorrow and then review, and we'll talk more about quiz situations and work situations and stuff tomorrow after we review before your next quiz. Okay?
Okay.
I'll see
Alrighty.
everybody tomorrow at 1.